Good morning. Apologies for my morning voice, but if I'm an astronomer, it's because I hate mornings. So I chose this job to work at nights, but as you can see, even an astronomer has to work at mornings sometime. And I'm sure you, you all have the same problem. I see smiles. So to make it up to you for getting you out of bed, I will take you on a trip today. This will be a very far away trip. We're going to go far away into the solar system. We're going to encounter some strange objects. We're going maybe even to run into some alien life, because we've all been talking about alien life and nobody has shown you any alien life, right, so far. So we'll see if we can get them to show up. I'm also going to say a few words about how we go about to get the information we need to look for habitable worlds in the solar system and even a little bit beyond. So I'm going to be talking about space missions, which is something that is very dear to my heart, because this is how we get close to the objects we want to study. So I'm, as I said, an astrophysicist. I work at Paris Meudon Observatory down there. But today we're going to go in exploring our solar system, and because a lot of people are interested in the telluric planets, which are absolutely of no concern to me, including the Earth, but I've learned quite a few things this past few days, which is very helpful for me. We're going to actually be more interested in the giant planets here, Jupiter and Saturn. And our solar system, as you know very well, is a highly diversified environment. So you have, on the one hand, the terrestrial planets, on the other hand, the icy giants here, Uranus and Neptune, and the gas giants here. And a lot of theories, you've heard about it also in the beginning of the week, are coming in now, new theories that can explain a little bit how our solar system formed the way it is and why we have the gas giants where we have them, contrary to what we find in some other planetary systems. So if I'm talking about other planetary systems, I'm talking about exoplanets. I'm sure you've all heard about exoplanets. Today it's not a myth anymore. We have several thousands of exoplanets discovered out there. These are planets that rotate around other stars than our sun, right? And today we have more than 3,000, close to 4,000 of these exoplanets discovered. So our solar system in itself is, as you see it here, and within it the giant planets that you see are also themselves quite different one from the other. You can see just in the pictures, but I'll say a few words about how different they are. They were first explored by the Voyager missions. So I'm sure many of you haven't heard or have heard about the Voyager missions. These are fantastic robots that we sent out in the 70s with the technology of the 60s, but managed to go through the whole solar system, go to the giants, go to the icy planets, and give us all the information we used to have before, including these 4 pictures that you see here, which were everything we had in our scholar manuals, at least when I started out in astronomy. Since then, we've done quite a lot more with space missions, but one of the most interesting features in our solar system is actually the satellites. The moons that we find around our planets, both around the terrestrial planets and around the giant planets. So we're going to be discussing satellites because, as you can see, there are several of them around all of the giant planets. Now, you've heard quite a lot about habitability since the beginning of the week. I am not a biologist, I'm not a chemist, not even a geologist, but when you do astronomy, and in particular when you're interested in astrobiology, from the perspective of an astrophysicist, you have to bring a lot of things together. You can't do it just by the schooling I have from the university, just about how stars work and how planets work. You have to have a little bit of geology, you have to have a lot of planetary atmospheres, how atmospheres work, you have to know a little bit what you can find out about chemistry, right? Not much about biology, but all of this comes together, and we need all of this to be able to explore what we call habitable worlds. But as far as I'm concerned, what is habitability for an astronomer? So you've heard of this before. Okay, we need water, right? And we're talking about life as we know it on our own planet, because I'll start extrapolating at some point, but for the moment I'm looking for life as we know it on Earth. So you need water, you need essential elements, and for me the essential elements, as you've heard before, are the schnapps. Okay, CHNOPS, you've heard about it quite a lot before. This in fact is the nutrients, it's what we need to eat, right, and to create our metabolism. And you need the chemical energy also for this metabolism. You need to have the energy sources that will enhance and will put in place the whole system and the metabolism that you need to create the living organisms. And something that people tend to ignore, but for an astrophysicist is very important, you need a stable environment. If your planet or your satellite or whatever your body is starts to disrupt, is in some kind of resonance, has strange properties, is rotating around a binary system, you know, with two stars, it's not a stable environment. So you need a stable environment. So these are the four conditions for me, and habitability is actually, for us astrophysicists, the measure of a planet's or a natural satellite's potential to develop and sustain life on or in. Okay, and so far you've heard about on, and so as you may have guessed, I'm going to be talking more about in. But this is actually the definition that we have today, and life may develop directly on a planet or a satellite, or be transferred. You had something before about the potential to have brought life, for instance, from Mars, the panspermia theory, things like that. And I don't care personally how life got there. What I care about, are there the conditions on this object to sustain the life? If it has emerged or if it has been brought there, is this a habitable environment, a favorable environment for life? So you've seen this before. It was shown, the habitable zone, in a previous lecture. This is the habitable zone as we have it in a traditional way, this blue area here. These are different stars, different brightness, different sizes, different magnitude stars. One is our sun here, and I've put here across the solar system, as you can see. And you've heard about the snow line and about where the water can exist in liquid form. And this is actually what represents the traditional habitable zone, is the area where we have liquid water possible on the surface. And this is what we call the surface habitats. In this area, anything that can be found could have liquid water on its surface. And lo and behold, the only planet we have in this traditional habitable zone today in our solar system is the Earth. There are theories about how this habitable zone could have moved on from the one side to the other side, that Mars could have been in the habitable zone in a previous life, and how life may have developed there with the liquid water on the surface. But today, the most you can find on Mars' surface, and even as far as I know, underneath the surface, are some small patches of water. Not much water, okay? So this is the habitable zone. The larger your star, the habitable zone, because you get more energy, moves outwards. If you have a smaller star, like the M dwarfs, for instance, or all of those stars that are very, very frequent and ubiquitous in our universe, the habitable zone moves closer. And this is one of the explanations we have as to why some of the new exoplanets that we find are very close to their stars, and they can still be in what we call a habitable zone, with the possibility of liquid water on their surfaces. So this is the traditional habitable zone today, and if you look in the solar system today, actually you have another category of objects. We call them the deep habitats. How do we run into these deep habitats? Well, one of the observations we got from one of the space missions were these geysers here. The geysers that you see here are emanating from a small moon called Enceladus. And this Enceladus moon is one of the moons. How many moons does Saturn have?
60-something.
Yes, 60-something. One of the 60-something moons, 63 actually if I'm counting correctly today. One of those moons is this Enceladus moon, very small moon, and we saw geysers coming out. And every model we have for 10 astronomical units where Saturn sits would tell you, no, 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 you can't have a habitable zone out there at 10 astronomical units, but you could have, according to this, pockets of liquid water at least, not to mention an ocean underneath the surface of Enceladus, because this is the only way you can get these geysers. And this has made people think that the habitable zone actually extends much, much further out with these deep habitats that may actually satisfy the 4 conditions that we have up here: liquid water, stable environment, essential elements, and energy. So the habitable zone is not restricted to the Earth's orbit. And this is something that people from the University of Nantes have looked very closely at to see how these conditions can be satisfied for the icy moons. In 2009, we did a paper that was trying to somehow put together the different categories that we could have as far as habitability is concerned, with Helmut Lammer and other colleagues. So on the one hand, we have the class 1 objects. This is the classical habitable zone, habitat suitable for the evolution of higher life forms on the surface. So we're all higher life forms here, right? On the surface, right? So this is Earth-like planet, completely Earth-like. Class 2, these poor things like Venus and Mars, who found themselves at the edge of the habitable zone at some point, or inside the habitable zone, but didn't manage to quite evolve as far as we have come. But we have the possibility that perhaps some microbial life has evolved there at some point in the past. And this is what we try to find with some of the space missions. And you may have heard about some of the samples we brought back, in which people like McKay and others have claimed to have found fossils from primitive life on Mars, for instance. Class 3 is beyond the ice line. You heard about the ice line. Water is not liquid anymore on the surfaces, and life forms may have evolved, but in this case, we're talking about populations under the surface in liquid water oceans that could exist and actually be in contact, direct contact with the core, with the silicate core of the planet. And this is important because, as you've heard, this is what happens on Earth, and this is a very important mechanism. Class 4 would be bodies with subsurface oceans again, but they wouldn't be in contact with silicate-rich sea floors. And this is where we find some of the icy moons that I'll be talking about. And if life evolves in these 2 new cases, it would be evolving without the sunlight underneath the surfaces. So in category 1, of course, we have one example, the Earth type, our own planet. You can see it here. We've discussed this before, but just to remind you some of the main characteristics that make it habitable: plate tectonics, water exists in 3 different states, liquid, solid, and vapor. Note that when we talk about water and we look at the Earth and Earth-like planets, something that people miss sometimes, it's that the total amount of water that you have, if you take the whole surface and all the oceans on the Earth, is only about 0.01 or 0.05%. It's a very, very small amount of water by weight that you have on the Earth. And if you notice the title of my talk today, it's called Water Worlds and Habitability. And when I'm talking about water worlds, I'm not going to bother with something with so little water inside, right? We're going to be talking about objects that will have much more water than that. Something like 10% of the total weight water, and I'll show you in a minute. But the Earth has other advantages. You've heard about the atmosphere. The atmosphere is there to protect us and to give us the nutrients that also come from inside. And we have the magnetic shielding, which is very important also to protect us from the solar wind and all the particles that could be damaging to life, and a good stability. Remember, we need a stable environment. So in the case of the category 1, we have the Earth. Category 2, here we have the as I said, the misfits, Mars-like, Venus-like, where time dimension is crucial. Again, due to migration or other theories about how our solar system formed, these poor planets may have moved inwards, outwards. There are theories about how Mars may have lost its atmosphere, and of course you know that Venus has also developed very strangely and very damagingly to life, thanks to a runaway greenhouse effect that made this atmosphere into the toxic, dense, wrong atmosphere that we have today. So their position within the habitable zone may have changed for this planet, Venus and Mars. They have very weak, if any, magnetic fields. In the past, they may have had magnetic fields larger, but today, very weak magnetic fields. The dynamical evolution has not gone the right way. Basically, there has been a lot of dynamical evolution. They've changed quite a lot. And the atmospheric loss processes is what made Mars the way it is today. So we're going to be looking at some of these things in other places. So remember, the stellar variation, the presence of a magnetic field, energy sources on the surface and elsewhere are essential elements when we're looking for habitable worlds in the solar system. And when we go out now, we're going to be looking at category 3 and 4. Again, remember, category 3 is where we have a liquid water ocean underneath the surface in contact with the silicate core. In category 4 is where we have a liquid ocean but sandwiched between two ice layers. So this is where we find ourselves now in this new region, the habitable zone, extended far beyond the snow line. We actually don't even know where this stops, and where we have the icy moons, Ganymede, Europa, Titan, and Enceladus. These are the moons from around Jupiter and around Saturn that you see here, who are archetypes of these habitable worlds, new categories. And how do we go about exploring these moons? So you see them here basically in scale, a little bit with the Earth. So these are large objects. These are not all small, tiny moons like Enceladus. And among all the satellites in the solar system, which is the largest one? Ganymede. And the second? And when we're talking about Ganymede and Titan, we're actually talking about bodies that are half the size of the Earth. They're larger than Mercury. So you can see these are really large bodies. You can see them here. In the case of the satellites around Jupiter, we've had some exploration before, essentially by the Galileo mission that did the exploration between 1995 and 2000. And in the case of the Saturnian satellites, we've had the Cassini mission that explored the system since 2004. So we'll start with habitats in the Jupiter system. The Jupiter system, because it's closer to us, it's supposed to be more easy to go to. You would have thought we would have had several missions there. But in fact, no. And it's a pity, because this is a very important system. You can see here how it has, all this largest, actually, body in our solar system, a giant gas planet. Of course, giant planets are of no interest to us as concerns habitability, because they have no solid surfaces. And their composition, as you can see here, is not exactly what we would expect if we wanted the schnapps to predominate. But it has one unique feature, and that's the huge magnetosphere. If you could see it in the solar system, Jupiter's magnetosphere would be the largest object you could see. It's not visible. It's the largest object we have to study in our solar system, this huge magnetosphere. It's 14 times stronger than the Earth due to the metallic hydrogen dynamics, the separation we have in the core of Jupiter. And of course, the Jupiter system has its moons. These are 4 of the moons. Do you know how they're called? Yeah, the name of the discoverer, the Galilean moons. Discovered more than 350 years ago, right? These are huge objects. You can see them here. This is a picture you can take with an average small telescope from the Earth, and you can see the 4 moons aligned around Jupiter if you have the right camera. And here you can have you can see some of the smaller moons in the Jupiter system. Here are the Galilean moons, but here you can see you have tons of little moons. As somebody said here, 60-something moons around Jupiter. And you'll see it's the same for the other gaseous giant we're going to see. So we've had 8 space missions to actually have performed 5 flybys of the giant planets, and one of them is the Galileo mission. Actually, it was launched in 1989, and it arrived and went into orbit in 1995 and ended its life in September 2000. And it investigated the giant planet and made a few flybys of the moons that you can see here, but it wasn't enough. And so this mission gave us few snapshots of actually what's happening in the system. We got some data from remote sensing, but very localized, essentially focusing on the planet. In situ sampling, that means looking very closely to some unusual meteorological sites, but we see that there are still a lot of things to do, like we're lacking coverage of the surfaces of many of the icy moons. There's a strong limitation in how we got information on the atmosphere of the planet, but also on the different moons. And we have now, of course, new instrumental techniques that would allow us to go much, much further in the exploration of the system than we could go in the 90s. So what emerged actually from the observations that Galileo made is that 3 of the moons there could actually, if you look also from ground-based measurements, be very, very important for habitable conditions in the solar system. And again, I have to insist that although about 70% of Earth's surface, I think, is covered with oceans, it only represents some 0.05%, right, of the total weight, of the total mass. And these are worlds that have what we call hydrospheres. Hydrospheres are these blue lines that you see that don't look very extended here, but they are the kilometers of water underneath the surface that we have detected with different measurements, including gravitational measurements, including spin changes, including the rotation parameters of these bodies, and so on, that indicate that the total weight here could be as much as 10% of the mass of the object. So these are water worlds, and one of them is, of course, Ganymede, the largest satellite in the solar system. It has a deep ocean that I've just shown you here, but it's sandwiched between 2 ice layers. So many of us have a difficult time realizing how you can put water between 2 ice layers. And I keep asking that question. But yes, you can. Geologists and chemists say, yes, you can. It all has to do with the pressure of the ice and how dense it is, and you can put it, and look, I can show you, and so on. So I trust them, because, you have to start somewhere. So yes, you can. And so you have this deep ocean. Another important feature we'll come back to is this internal dynamo and an induced magnetic field. This is a unique feature in the solar system. You've heard about the magnetic field and how rare it is in the solar system. Actually, there are only 2 other bodies besides Ganymede who have this magnetic field, this dynamo. Who knows? Of course, the Earth and Mercury. That's right. So you see, it's not all spread out throughout the solar system. This is a unique feature. It has very rich crater morphologies, and it's the best example of a liquid environment of category 4, as I mentioned before, sandwiched between ice layers. Very, very unique object in the solar system. We also have Callisto there. I've put them in size. Best place to study impactor history, because you'll see the surface is really terribly affected by impacts. There's a question about differentiation. You see this body has differentiated. You have the core here, you have the mantle, the ice layer, the hydrosphere, another ice layer, and the crust. In the case of Callisto, we really don't know what the interior is like, if it has differentiated, but we think in this non-active body, meaning that we don't see a lot of things happening on the surface, because if a body is active, you get resurfacing from the inside, and the surface changes with time, right? We haven't seen that on Callisto, and we don't know if it's differentiated, but we still think that there may be a hydrosphere. It's what you see here in a gray color. But we still need to go and look at it as a witness of early ages. And this is Europa, finally, and everybody has heard about Europa. Europa is the satellite that geologists have so much fun with that I think we should remove it from the solar system. It's indecent to have so much fun with it for you geologists. So you see, look at the surface. It's got cracks, it's got white areas, it's got red areas, it's got dark areas, it's got canyons, it's got resurfacing, it's got everything a geologist could dream of. And the fun they're having is because trying to piece together what's going on the surface, they have come up with this hypothesis that there has to be an undersurface liquid ocean, and I'll show you why. In a little while. It's supposed to be an active world. Everything we see on the surface indicates that it is an active world because the surface has undergone recent processes that make it the way it is today. And it's again a best example of category 3, a liquid environment in contact with silicates. And many people probably know the fact that you have these tides. If you're close to your planet or to the sun, you suffer. Look how Io suffers. Io, this poor little moon, has got 400 volcanoes on its surface. Everything on the surface is melt. Everything from the interior that comes out on the surface is burning up. So this poor satellite is so close to Jupiter that actually it's burning up. No, of course, no capability for habitability or anything else. It's just trying to survive without exploding. And then you have Europa, and again, as I mentioned, you see these indications on the surface of recent processes, and we think this has to do with the tides and with the influence of the Jupiter, and all of these dynamic movements are due to that. You also have Ganymede further out. Possible activity in Callisto is it's because it's so further out, the furthest out of these Galilean moons, that has probably survived all of these processes from the inside and from the influence of Jupiter. The other thing that you get if you're very close to Jupiter is the radiation effect. And this is going to come back because the radiation effect is something that affects the surfaces also. So anything you could have on the surfaces, if you are very close to Jupiter, won't survive a long time because of the radiation effect. And these are the interiors for these moons, and you can see again here how we have this possible hydrospheres and the differentiation occurring on Europa and Ganymede, and not so much possibly on Callisto. So we're very hot in the interior, very radiation affected if you're close to Jupiter. This is Europa close up. Remember, I told you about these cracks and the streaks and that we see on the surface. We have some impacts, but most of the craters are covered. And geologists will tell you if you have a surface where the craters are filled in and they're covered, this is a young surface, and this means basically that something has come from the interior to cover up. It could be erosion processes also, but sometimes you get something from the interior that comes and covers your craters. And the less craters you have on the surface, the less impact features you have, the younger your surface. And I'm sure I'm schematizing here, and the geologists would jump up and down to tell me something more precise. But basically, I think I understood this is what it is. And when you have features like this here, they try to put them together, and they say that there is evidence of tectonics in Europa on the one hand, and also on the other hand that all of these movements happened because of an underlying liquid water ocean that pushed the different areas on the surface at a moment where they were still soft, got them together or opened them up and separated them, and they have very strong evidence by putting together the streaks and the cracks to show that some of these areas were together before and were separated, and vice versa with geological processes. So we don't know exactly what happened, but there are hyperspectral evidences indicating that there is a liquid water underneath Europa's surface. The other thing we don't know is we don't know what the surface is made of. We have no clue. We've tried different things. You can see here, this is the Europa icy, that's the white patches, and the Europa non-icy, that's the darker patches in spectroscopy. And then we have tried different things, epsomite, other kinds of pure ice, pure water ice, and so on. There is, of course, pure water ice on Europa's surface. I mean, it's covered, all the moons have it. But exactly to fit the spectrum is not possible yet with the mixtures we've tried. So really, this is a case where we need to get a closer look. I'm talking about images from the Galileo mission, which did only a few flybys of Europa and took these images with technology dating back to the 60s. So Europa, very, very interesting. And this is the schematics that shows how this ocean, undersurface ocean on Europa, can actually operate by different mechanisms. We have convection in the upper layers. There could be some radiation-produced oxidants on the surface of Europa. The temperature is about 100 Kelvin, possibly melting in the ice that would lead some of the things we find on the surface and depose them into the salty ocean. The temperature here is 270 degrees K. Hydrothermally produced reductants also, because we are in contact with the rocky mantle. Again, hydrothermal circulation. This is why I was so interested about the hydrothermal processes on other objects. You can have temperatures as high as 1500 K down here. And this isn't something that actually bears to the 4 ingredients for life I mentioned before. You have a water, you have warm, salty actually water measurements that we have from spectroscopy in Europa. How about essential elements? You could accrete something like CO2, for instance, from impactors. But again, as I said, the radiation would destroy organics in the upper 10 centimeters, so they would have to find a way of going deep inside very, very quickly and hide, preferably find a way into the ocean. Chemical energy is there. We have also radiation of H2O to produce the oxidants, but the mantle contact down here creates conditions for possible serpentinization and possible hydrothermal activity, and it's a relatively stable environment. The large satellite retains the heat, but we don't know if all this activity is steady state in the inside. So this is, again, showing some of the things we think might exist in Europa. And I think I'm going to try and show you now something that actually might help you imagine a little bit better what's going on this world.
Europa orbits Jupiter once every 3.6 days in an egg-shaped path. The gravitational pull from Jupiter changes constantly, stretching, then compressing Europa. This process is like kneading a piece of clay to make it warm and soft. And the heat produced may be enough to melt the underside of the ice sheet, creating a hidden ocean of liquid water, protected from the vacuum of space by the solid ice above. If so, there could be aliens living here. Creatures that have evolved to exploit this dark and ancient water world. I think it's even reasonable to guess at some of their physical features. Aliens here would probably swim in a similar way to our own ocean life, since liquid water is the same stuff everywhere. They might use chemicals in their skin to generate their own light, as many deep-sea creatures do back home.
So these are the chemiotrophs, right? Remember, we discussed this the other day and you heard more about it previously. And so now you know what alien life would look like, at least on Europa. Don't ask me why only 3 legs. I have no clue, or 3 tentacles, I don't know, maybe they have more. But, okay, so this is serious. It had some of the properties that you think might exist in the bottom of oceans. And again, as I said, I'm not looking for life myself, but I thought you might get a glimpse. The other object, of course, is Ganymede. And again, we mentioned that there should be liquid water underneath the surface. The question about the chemistry is, because we're not in contact, this ocean is not in contact with the silicates, how important is it to have this contact? Is the heat transfer that it gets from the inside, from the interior, from the tidal forces and from Jupiter enough? And it's definitely a stable environment here. And again, I have a small movie.
Jupiter, the largest planet in the solar system, comprised of enormous amounts of hydrogen and helium, the equivalent of 318 times the mass of our Earth. It is home to a vast variety of natural satellites, some having distinct and fascinating characteristics. But one of particular interest is Ganymede, named after the son of King Tros in Greek mythology, whom Jupiter took with him to Mount Olympus and granted eternal life. Ganymede is the 3rd Galilean satellite and 7th moon out from Jupiter. Having a diameter of around 5,000 kilometers, it is slightly larger than the terrestrial planet Mercury, also making it the largest moon in the solar system. Like our own moon, one side is always facing the planet. However, Ganymede completes a full revolution every 7 days and 3 hours. Our knowledge of this satellite comes from several probes which were sent during the 1970s through to the 2000s. These craft made multiple flybys and passes which enhanced our knowledge of the satellite. They gave us information about its size and composition and showed us that it was larger than Saturn's moon Titan, which was previously thought to be larger. They revealed that the crust of Ganymede was made up of water, ice and silicate rock. Other elements such as carbon dioxide, sulfur dioxide and other organic compounds are also present. The surface is a combination of 2 different types of terrain, one darker, ancient, heavily cratered region, and one lighter, somewhat younger area scarred with an abundance of grooves and ridges. The formation of these grooves is up for debate, but it is generally accepted that the terrain is a result of tectonic activity and perhaps cryovolcanism. The moon would have undergone stress as it passed through different gravitational fields produced by other moons and the immense tug of Jupiter itself. Interestingly, some salts are also present, which are thought to have originated in Ganymede's subsurface ocean. Like Europa, Ganymede has an ocean deep beneath its crust, but unlike Europa, Ganymede's ocean is salt water. The ocean is thought to lie about 200 kilometers beneath the crust, but Ganymede does have an iron liquid core, which may allow for the formation of hydrothermal vents, an energy source for evolving life. Another interesting aspect about Ganymede is that it has a substantial magnetosphere, one of the few objects in the solar system that possesses one. This is another factor that may contribute to the evolution of life, as a magnetosphere can provide shielding from harmful electromagnetic radiation from the Sun. Life on this alien world would be very different from anything we're used to. It would have had to have evolved relying on a different energy source and adapted to living conditions with extremely low light. If life has evolved on Ganymede, it will be very strange. There are no current missions to Ganymede due to lack of funding, although there are missions to Jupiter's other moons. Until we send a craft down to explore this intriguing world, it will remain a mystery.
So now we've got 2 alien life forms out of the way, and you've heard about how this object needs more investigation, if for nothing else because of all the different features, unique features that it boasts. So for instance, the induced magnetic field that you heard, the real dynamo inside this this satellite is composed of 3 different parts. There's an induced magnetic field from the interaction of the Jovian magnetosphere with a conducting layer, probably the ocean. There is an internally driven dipole magnetic field and the interaction of Ganymede's mini magnetosphere with Jupiter. And to separate them, it's really complicated. You heard about also the geology activity, the indications for younger surfaces with perhaps outflowing from the interior and darker, older terrains for which we have lots of questions still. But you heard the poor guy saying, we need to go back. Why are there missions to all the other moons and not to this one? Well, we have an answer to the question, and this is the JUICE mission. Who has heard about the JUICE mission? Okay, now I can skip 20 view graphs and go right to the end. I apologize for the name, JUICE. We were sitting with the team there and we had some beautiful names, Laplace, you know, this and that, wonderful names. But this mission has a strange story because it started in cooperation with the United States. It was called the EJSM, Europa Jupiter System Mission. It had to have 2 orbiters, one to Europa and one to Ganymede. And for reasons I won't detail here, but if you get me over a drink at some time, I'll explain to you. The US decided to withdraw and do their own mission to Europa, which hasn't happened yet. But in the meantime, we picked up the pieces and we went on with our orbiter of Ganymede, and we had to be really quick about finding a name. And JUICE stands for Jupiter Icy Moons Explorer. It's the best we could do at a fast time. And so we had to build this orbiter from scratch and present it to the European Space Agency and say, it's worth going just to Ganymede. And they said, why? And I said, I'll show you a movie, like the one before. And so, no, but we had so many good arguments, scientific arguments, why we needed this mission. Some of the themes that were of importance to European space agencies, the emergence of habitable worlds around gas giants, and the Jupiter system, of course, studied as an archetype for gas giants. Habitability was extremely central to this mission. And to look for all these criteria I mentioned before, looking for what are the conditions for planetary formation and emergence of life, and how does the solar system work. And so we put together this orbiter that has been selected. It's going to be the first large cosmic vision program mission. It's a single spacecraft. It's going to do investigations from orbit and flyby trajectories, synergistic and multidisciplinary payload. And it's a European mission with a strong international participation that's actually going to do a thorough study in the system, looking at all of these topics here, the planet, of course, the moons, rings, and the magnetosphere itself. You have the interior to look at, the subsurface, geological processes, atmospheric processes, the plasma, as I mentioned before, extremely important, habitability, and the link to exoplanets. And all of these things are going to be studied by the JUICE mission, and here are the main features of the spacecraft design. You have the mass here, 5 tons in total. It's going to be launched on Ariane 5, unless we get an Ariane 6 by that time and we can fit it in there. But for the moment, Ariane 6 seems to be a bit tight mass-wise and weight-wise. We're going to have a payload of some 200 kilograms, a 3-axis stabilized spacecraft. The power is the solar arrays you see here. We have a high gain antenna of 3 meters, and the data return is quite sufficient for the measurements we want to make. But the important part in a mission is always the payload. And you can see that we managed to engage many, many countries within Europe for the instruments that are on board JUICE. You don't get this kind of large missions often enough that you can just ignore the opportunity to be on board and bring your science, your expertise, and your instruments. And you can see several countries here for a full range of instrument types. Here is a more detailed view graph looking at the camera system, a sub-millimeter wave instrument that's going to be making measurements of the atmosphere, essentially complemented by the MAGIS instrument. This is an imaging spectrograph that will also make a lot of measurements in the near infrared range, a laser altimeter, an imaging spectrograph in the UV this time. This is provided by the United States. It's the only instrument we have on board from the United States, just to show you we don't bear grudges, you know. They wanted an instrument on board, they got it. And we have a nice penetrating radar, extremely important. We are going to be looking at places where you have a lot of ice. You need a nice penetrating radar. I mentioned the magnetosphere. Of course, we need a magnetometer. We need gravity, geophysics, and this kind of measurements, radio tracking. There's going to be a particle environment package. There's going to be a radio and plasma wave investigation instrument. And finally, a planetary radio interferometer and Doppler experiment. All of this payload is going to come together behind a mission that is going to launch in 2022. There is a backup window for August 2023, but we would much rather lift off in 2022. It's going to take about 8 years to get there because we're carrying a huge payload. The heavier you are, the more time it takes to get there. It's going to go into orbit insertion around Jupiter for 11 months. We have 2 Europa flybys planned. You can see them here, going above regions of Europa that are considered today to be of particular interest. They're called chaotic regions. Chaos, these are areas where we think the ice crust is shallower, actually, thinner than in other areas around Europa. This allows for the radar, for instance, to go inside and make measurements of the liquid water ocean in a much better enhanced way as to where you have a very, very thick ice layer to go through. So these regions here are regions that we call active areas, and so we're going to be looking at these regions. After those flybys, we're going to do a reduction of speed by doing several flybys on elliptical orbits around Callisto to get gravity assists. And then we're going to transfer to Ganymede. Ganymede is the essential target of this mission. Remember, we're going to go around Ganymede and make this kind of orbits, end up within a circular orbit at about 5,000 kilometers, then go down to 500 kilometers, and we're hoping to even go further down to 200 kilometers circular. And do you know how we're going to end up? Crash where? We're going to crash on Ganymede. What? Who has a problem with crashing on Ganymede? So there's, okay, we're going to kill the ions. All right. I'm glad you didn't say we're going to kill the life there. No. We cannot crash on Europa. You know why?
You want to make a big hole to dive in it?
What are you talking about? Which moon?
The moon, Ganymede is icy, right?
Yeah, because I was asking why you cannot crash on Europa because of planetary protection categorization. Europa is considered to be a place where life could exist close to the surface. In the case of Ganymede, because you have this huge ice layer, it's not considered possible that even crashing a spacecraft there would damage any life that would exist in the inside of the ocean. So today, we can still crash something on Ganymede. Now, in a few years down the line, and this is why we're in a hurry to lift off in 2022, the American government is going to come and say, no, we've decided we're going to change the categorization, you can't go crashing on Ganymede. In which case, we would crash, of course, into Jupiter.
Are you going to measure something also while crashing, or are you just going to crash because you can?
We're going to crash because we can't leave it there going into orbit, but we're going to crash also because we are going to make measurements. Probably during the descent, because nobody can guarantee that we will survive once we've crashed. But all the way down, we're going to be able to send back measurements very, very close to the surface. You're going to say, well, if you're at 200 kilometers, you're already very close to the surface. But the measurements you can do in situ, really very close up, are not compensated by what you can do at 200 kilometers of altitude. So this is something that really is very important to know, that this mission is going to, everything you crash, well, I shouldn't say it this way, but in any case, there's a positive side on crashing something, is that you can make measurements where you've crashed, and you'll see it when we'll discuss the Saturnian satellites, that being on the surface is completely indispensable in getting the ground truths for some of these bodies. So we think in the case of Ganymede, because we're not going to damage anything, and if we get all of these measurements, including if we have managed to land on the surface. So this is the JUICE cruise, and you can see how we've made several flybys of the Earth and of Mars, and here's when we get close to Jupiter. Because we're going to get all of these measurements, it's something that will really enhance the mission by a factor of 2 or up to 4. So we're really very keen on trying to get these measurements on the surface of Ganymede. So in the moon's flybys, I've mentioned the Europa flybys over these chaotic regions that are called Theta and Thras Macula. You can see here what is a Europa flyby. So note the date. We are 13 February 2031. Mark it on your calendars. You see where you are there. And we're going in with our mission. We've just gone very close to Europa, and now I'm going out again. So why aren't we, I said we couldn't crash, but why am I not staying in orbit around Europa? I'm going to go into orbit around Ganymede.
Not enough fuel to do both?
No, we have fuel. Remember what I said before? Radiation. If you stay in orbit around Europa, you're going to kill all of your instruments. It's the reason why the Americans couldn't get the orbiter around Europa. They realized the radiation effects would not allow for an orbiter to go into orbit around Europa. The mission the Americans currently have in plans, I'll show you in a minute, is flybys. You go in, you fly out immediately. Get your data, grab it, go out. Even if you do 40 flybys, it's okay. If you go into orbit, you kill your mission. This is why you also don't know how to do a lander on Europa.
Where does this radiation come from? Is it reflected?
Jupiter. Jupiter's... Yes. Yes. It's so strong. Remember I showed you that diagram with the 4 moons, and I said Europa is the second one. It's too close to Jupiter to do anything.
So you're going to switch off satellites when you pass over the Europa?
I'm sorry?
So you're going to switch off satellites when you pass by the Europa?
No, we're going to have our instruments turned on, but as I showed you, we're going in, and then we're going out immediately. We're doing flybys that are very short duration close to Europa. We have calculated very precisely how close we can get for how much time and how fast we need to move out. So these are going to be 2 flybys because we need to be very careful of our mission, because the main object, of course, is Ganymede. So we're only going to do 2 flybys. when we separated from the American orbiter, they could have done another orbiter to Europa immediately. You know, this was a few years back, 2010, right? We're 17. They haven't, because they don't know how to do an orbiter around Europa. The radiation field is just too important. So they're going to do a mission, but with just a few flybys. And did you see that, how we're going to do the Ganymede orbit insertion? So this is Ganymede, and we're getting closer. And we're going to do elliptic orbits, and then we're going to go circular. There's Jupiter in the background. You go once, you go twice, an elliptic orbit. And then you know you don't crash. You're actually into orbit now. And so JUICE is going to do a lot of science investigations. As I mentioned before, for the emergence of habitable worlds around gas giants, we have Ganymede as a planetary object, possible habitat, studying all these unique features, including the ocean and the internal dynamo. Europa's recently active zones. Is this an active world? An ocean in contact with silicates, much more familiar to what we have on the Earth. And Callisto is a remnant of the early Jovian system. The impactor history, what is the differentiation like and weakness for early ages? And for Jupiter's system, as an archetype for gas giants, we're going to be studying the Jupiter atmosphere, fluid dynamics, composition, and so on. The magnetosphere I showed you before, the largest object in our solar system, the astrophysical mechanisms, and the giant particle accelerator. And for the satellite and ring systems, a very important thing is the tidal forces. Again, this is how you get your energy in many cases. The Laplace resonance among the three Galilean moons, Io, Callisto, and Ganymede. The electromagnetic interactions to the magnetosphere and the atmosphere of Jupiter. So this is going to be a very, very thorough investigation of the system. Among other things, of course, we're going to look at the Europa to study those recently active regions. And the important thing here is the spatial resolution we're going to get, the conditions for the observations. And these are the chaotic regions I mentioned before, where the ice crust is thinner, and you can get to the water much more easily than in other places here where you have thicker ice layers. Look at the active processes on the surface and the tenuous atmosphere you have around Europa and Ganymede, and all the things that you can find on the surface. And of course the question being, how can these things from the surface go down into the ocean and create habitable conditions? And this is one of the things that we need to answer and look at the organic and inorganic chemistry, because remember, liquid water alone is not sufficient. The relation to geologic processes, the radiation effects, and what are the exogenic materials that come and hit the surface? Do they survive? And how can we understand the habitable conditions on Europa? Formation of surface features, recent or current activity, characterized candidate sites. For future in situ exploration, the Russians, the Americans insist that we really have to go back there at some point and really make in situ investigations. The way today would be to put a very thick shield around the instruments if you want to land something. But that would add so much weight to your mission that you would probably be able to fly one or two instruments. One other solution is a penetrator. I don't know if you've heard about penetrators. These are, the machines that you send in there. They crash through the ice. They find themselves below the 10 centimeters, of ice that I mentioned are very not life-friendly. And then they can make some measurements. And this is actually an idea that could be viable for Europa, and people are studying that and making proposals. So we'll see what happens in the future for landers, but for the time being, the JUICE mission is going to do a Jupiter tour, look at all the icy moons, and again, in comparison to what Juno is going to do. As far as Jupiter is concerned, it's these high inclination trajectories that we managed to make that will give us information on the auroras, for instance, on Jupiter. That's something that Juno is not going to be able to do. So we're going to complement for the planet itself. But because JUICE is really centered on the icy moons, this is what it's going to be extremely, extremely important to get. And so we'll have an exploration of the Jupiter system for the planet, the magnetosphere, coupling processes, and the satellite system, all of this coming together. But of course, as far as habitable worlds are concerned, we have Ganymede, Europa. So in the case of Ganymede, with the liquid layers trapped between two ice layers, what are the conditions inside the liquid water? Because this is actually one of the most common habitat in the universe, the water worlds. This is really a category of planets and exoplanets, really very broad, that hasn't been studied so far extensively. And so we'll characterize Ganymede. In the case of Europa, you have contact with the silicates here at the seafloor. This is possible apparently for Europa and Enceladus for very small bodies. And are the surface active areas, can they be in contact with the deep interior and the water ocean? So we have a contractor now. It's Airbus for JUICE. And Airbus has put together this very nice little movie for advertising what they're going to do. So if we can... You also need to be sure that you get the maximum out of your mission. So we're going, all of these connect very tightly to the universe exploration, where you have this plasma controlled by the fundamental electromagnetic force, and the sun and the stars influences the environment of the Earth around other planets. So we're going to be looking at getting information about accretion disks and pulsars from all of these. What are the fundamental processes that transport, convert, and release energy in plasmas? So this mission is really a first. It's going to be addressing the emergence of habitable worlds. As I said, we're going to learn so much more for the gas giant Jupiter and the icy moons. We're going to do comparative study and 2 classes of planetary atmospheres, as I said, class 3, class 4, magnetosphere, couplings with the Jovian system, and conjunction, of course, with ground-based observations. You've seen before, I've shown you how many different countries are involved in this mission in Europe, but also abroad, and you can see all the names of the different missions here, 28 different missions. So at the same time, I mentioned before, the United States is putting together a mission. It used to be called CLIPPER, because they're going in, out, right? So it's not an orbiter. It's going to be doing 45 or 47 flybys of Europa, very low altitudes in some cases, and then you go out again, as I mentioned. There are 9 instruments selected already, because in the United States you get your instruments before your mission is even decided or adopted or selected. So this is a mission, bear in mind, it's in study phase. It has not been selected. It's not necessarily going to happen, but they have the instruments. They're looking at how this is going to be studied. You can see some of the instruments here complement or duplicate what we have on JUICE. But again, JUICE is only going to do 2 flybys of Europa. It's mainly headed for Ganymede. But the curious thing is that in the United States, you have to go and do what the people who give you the money for it tell you to do. In this case, it's the government so far that pays the different PIs and the mission, and the government has said that they want to launch in 2022 on an SLS, the platform, the huge platform that can carry 50 tons of material. I don't know if you've heard about it, but that is not certified. It's not built yet. It's something that is being studied, so we don't know if this is going to happen by 2022. If it happens, the cruise will be 2 years. I love this concept. 2 years to get to Jupiter instead of 8. So if they manage to do that, that means that they will get there before JUICE, right? So we then, with our poor 2 flybys of Europa, but somehow I have still my doubts about these 2 years. If not, they'll take 7 years like everybody else. They're still looking at the mission concept and the architecture, which actually may push the launch to 2025. They have the same duration for the nominal mission, and you can see the concept here. They have very pretty pictures and so on. And the multiple flybys, I explained why they have to do that. And there is discussions about elements that ESA could put on board, but for the time being, this is a concept that is going to be studied further in the years to come. So basically, rendezvous in 2030 for all of that. Thank you.